Welcome to Lab 3 of our Signal Integrity Basics series. This session focuses on termination, a critical technique for managing signal reflections in high-speed PCB designs. Proper termination is essential for maintaining signal integrity and ensuring reliable system operation. Our objectives for this lab are to utilize the digital oscilloscope for measuring positive overshoot, to employ the terminator wizard within HyperLynx to calculate optimal termination values, and to gain a practical understanding of implementing both series and parallel termination schemes. As signals propagate along PCB traces, they behave as electromagnetic waves traveling through transmission lines. A fundamental challenge arises when these signals encounter an impedance mismatch. A portion of the signal energy can reflect back towards the source. These reflections are detrimental. They can distort the intended waveform, degrade the clarity of an eye diagram, and introduce timing uncertainties. Termination is the method employed to mitigate these issues by matching the impedance at the end of the transmission line to its characteristic impedance. This ensures that signal energy is absorbed cleanly, preventing reflections and preserving the signal quality. To start, we will invoke Siemens HyperLynx SI, navigate to your SI Basics lab directory via Windows File Explorer, then double-click to the Launch HyperLynx SI icon. For exercise 1, we will open the schematic file for series termination. Select Browse, Line Sim Projects, Open Schematic. Then locate your working directory in HL Workshops, find the series term.ffs file, and click OK. With the schematic loaded, let's observe the initial signal behavior. Access the digital oscilloscope by selecting Signal Integrity Interactive Oscilloscope. Once the oscilloscope opens, click Start Simulation. Once the simulation is finished, select the latest waveform for U2.1 from the waveform selector at the bottom of the oscilloscope. Then, from the measurement section, choose Positive Overshoot. Note the measured overshoot and any visible ringing on the waveform. This baseline measurement illustrates the signal integrity issues present on the unterminated line. Now, we will introduce a series termination resistor at the driver end of this net. First, return to the schematic window, then click on the current line segment between U1.1 and TL1 and delete it. From Schematic Symbols Passives, select the resistor. Click and drag that resistor symbol into the position between U1.1 and TL1. Connect the components by either dragging from the circular pin of the driver to one side of the resistor or by aligning the two circles and dragging. For now, let's leave the resistor value at 0 ohms. We will use the terminator wizard to determine the optimal value. Series termination is typically placed close to the driver. Its purpose is to match the driver's output impedance to the characteristic impedance of the transmission line, thereby preventing reflections from the source. This is particularly effective for point-to-point connections. To calculate the optimal resistor value, we will use the Terminator Wizard. Select Signal Integrity, Interactive, Optimize Termination. In the device pin selection, choose U1.1, then click OK. The Terminator Wizard will then analyze the net and present a suggested resistor value. Observe the information provided, including the driver impedance, Z source, and the line impedance, Z naught. While the simplified equation for series resistance might suggest that series resistor equals Z naught minus Z source, you will notice that the suggested value from the wizard does not exactly match. This discrepancy arises because the wizard considers the effective Z naught, which accounts for the parasitic capacitance on the line, not included in the simplified calculation. This capacitance is crucial for accurate signal behavior, making the effective Z naught a more precise parameter for termination design. For this exercise, set the apply tolerance to 1% and note any minor adjustment to the suggested resistor value. Click Apply Values to assign this calculated resistance to R1, then click OK to close the wizard. Let's now observe the impact of our series termination on this signal. Return to the digital oscilloscope by selecting Signal Integrity Interactive Oscilloscope once again, then click Start Simulation. Once again, select Positive Overshoot from the Measurement selection. Compare this new measurement with our initial baseline. You should observe a significant reduction in positive overshoot and ringing, indicating a substantial improvement in signal integrity. This demonstrates how effectively series termination absorbs reflections at the source. While series termination is highly effective, it is not the only technique. We will now explore parallel termination. The primary goal of parallel termination is to match the transmission line impedance at the receiving end, absorbing the signal energy and preventing reflections back towards the source. Ideally, signals traveling down the characteristic impedance of a transmission line should encounter an impedance of the same value at the receiver. The effective impedance at the receiving device is the parallel combination of the termination impedance and the input impedance of the receiving device. Invoke HyperLynx SI again by navigating to your SI Basics lab directory, double-clicking on the Launch HyperLynx SI icon. This time, we're going to browse to the parallelterm.ffs file. Once the project is open, we'll establish a baseline once again. Access the digital oscilloscope via Signal Integrity Interactive Oscilloscope, then click Start Simulation. From the dropdown, select the latest U2.P003 from the waveform selector, and then Positive Overshoot from the Measurement section. Note the overshoot and ringing before any parallel termination is applied. This will serve as a reference point. Minimize the digital oscilloscope and return to the LineSim schematic window. We will now add a resistor in parallel at the receiver end of this line. From Schematic Symbols Passives, select the resistor and click and drag the resistor symbol to position it between TL1 and U2.P003. With the resistor selected, press and hold Ctrl-R to rotate it 90 degrees. Next, from Schematic Symbol, Power and Ground, add a ground symbol directly below the resistor. As before, connect the components by dragging from the pin of the transmission line to one side of the resistor, and from the other side of the resistor to the ground symbol. Ensure the connections are complete. As we did with the series termination, we'll leave the resistor at 0 ohms for now, as the Terminator wizard will calculate the optimal value. Run the Terminator wizard again by selecting Signal Integrity Interactive Optimized Termination. The wizard will analyze the net and suggest a resistor value. Click Apply Values to assign the suggested resistance to our newly placed resistor, then click OK to close the wizard. Finally, let's assess the effectiveness of our parallel termination. Again, return to the digital oscilloscope, then click Start Simulation. Select Positive Overshoot from the Measurement section. You should observe that the positive overshoot and ringing have been significantly minimized, demonstrating the successful application of parallel termination. This confirms that reflections at the receiver end have been effectively absorbed. In summary, we have successfully implemented and analyzed both series and parallel termination techniques within HyperLynx SI. The choice between termination methods depends on various factors, including available board space, required signal edge rates, timing constraints at the receiver, logic thresholds, and power consumption requirements. The Terminator wizard serves as an invaluable tool for guiding users towards optimal termination solutions. It's crucial to remember that the placement of the termination resistor is paramount. For series termination, it should be as close as possible to the driver, and for parallel termination, it should be as close as possible to the receiver. This concludes our exploration of termination techniques. Understanding these methods is fundamental to achieving robust signal integrity in your designs.